Hello everyone, and welcome to my channel. Today, we're diving into 4 real-time communication technologies: HTTP polling, server-sent events, SSE, WebSocket, and WebHooks. These technologies play a crucial role in our daily online world. Ever wondered how they work? What are their strengths and limitations? Or what scenarios are they best suited for? If these questions catch your interest, then this video is made just for you. In this video, we'll break down how these technologies operate and use interactive diagrams to help you understand how they facilitate real-time data transfer behind the scenes. We'll also explore the advantages and limitations of each technology, their appropriate use cases, and demonstrate how they're applied through real-life examples. Whether you're a developer, a tech enthusiast, or just someone curious about technology, I'm confident you'll find valuable insights in this video. So, stay tuned as we delve deeper into these fascinating technologies. Let's first explore HTTP polling, a fundamental method for real-time communication where the client periodically sends requests to the server to fetch the latest data. There are 2 main types of HTTP polling: short polling and long polling. Short polling works quite straightforwardly. The client regularly sends HTTP requests to the server to check for new data. The server, upon receiving each request, immediately returns a response, regardless of whether there is new data. Here's how short polling works. The client sends a request to the server at set intervals, say every 15 seconds. When the server receives a request, it checks for new data and sends it back if available. If not, it sends an empty response. The client processes any received data and then waits for the next interval to send another request. This method offers near real-time data retrieval, meaning there can be some delays. Long polling improves upon short polling by reducing the number of requests. In this method, after the client sends a request, if there is no new data, the server doesn't immediately respond. Instead, it holds the request open for a period until new data becomes available or a certain timeout limit is reached. Here's the interaction for long polling. The client sends a request to the server. If there's no data, the server doesn't respond immediately, but waits while keeping the connection open. Once new data is available, the server responds immediately. If a timeout occurs, for example after 100 seconds with no data, it sends a timeout notification. The client, upon receiving data or a timeout notification, immediately makes another request. This method allows clients to receive updates in real time. Now, let's examine the advantages and limitations of HTTP polling. Advantages. 1. Wide compatibility. Based on HTTP protocol, polling is supported on a broad range of platforms. 2. Easy implementation. It's straightforward to implement without the need for special tools or libraries. 3. Timely communication. Short polling offers near real-time communication, while long polling provides actual real-time updates. Limitations. 1. Resource consumption. Short polling can lead to numerous ineffective requests, wasting bandwidth and server resources. Long polling reduces the frequency of requests, but still involves repeated connections. 2. Data delay. With short polling, updates might occur between requests, leading to delays. 3. Server load. Although long polling reduces the number of requests, maintaining open connections under high concurrency can burden the server. Suitable scenarios. Considering these points, both short and long polling are viable options for scenarios like user notifications or status updates, where there is limited concurrency. Short polling is more suitable for scenarios that do not require stringent real-time updates and have small data volumes. Long polling is better for scenarios needing real-time updates. In practice, the polling intervals and timeout settings should be adjusted based on business needs to balance resource expenditure and response timeliness. Now let's look at 2 typical cases of HTTP polling in action. Case 1. Configuration Management System. The first example is a configuration or feature flag management system, typically comprising a feature flag service and a database. Administrators can modify settings through a user interface, with changes saved to the database. Many clients need to sync these settings quickly. HTTP polling, particularly short polling, is suitable here. Clients regularly check for configuration updates to ensure they receive the latest settings. For more real-time synchronization, long polling could also be used. This example demonstrates how HTTP polling can facilitate timely synchronization of configuration data, providing a simple and easy-to-implement solution suitable for scenarios with limited concurrency, small data volumes, and infrequent updates. Case 2. Social Sharing App. Consider a more complex application, the back-end design of a social sharing system. Users post pictures or videos to social sites, often a time-consuming operation. To avoid blocking the system, we use an asynchronous system design. The backend consists of several parts. 1. Post service handles API requests from the front end, including job submissions and job status queries. 2. Post job consumer processes job messages, publishes content to social sites, and updates job status. 3. Message queue (MQ) manages the asynchronous handling of jobs. 4. Database (DB) stores job details and their processing status. Here's how it operates. 1. User initiate post request from the front end. 2. Post service receives the request, converts it into a job, stores it in the database, and sends a job message to the MQ. 3. At this point, the job has been successfully submitted, and the post service returns a job ID to the front end. Since inserting data into the database and MQ involves lightweight operations, the job submission process is quick and does not block the front end. 4. The front end, having received a job ID, periodically polls the post service to check the job's execution status. 5. If the job is queued or in process, the front end receives an in-queue or in-process status. 6. Concurrently, post-job consumer picks up the job from the MQ, begins publishing to the social site, and updates the final status, success or failure, in the database. 7. After one or several polling rounds, the front end eventually receives the result status of the posting operation. This design, combining asynchronous operations with polling, not only avoids blocking in post-service, but also supports near real-time responses on the front end. It is particularly suitable for handling long-running back-end tasks while maintaining a smooth user experience on the front end. Now let's explore server-sent events. SSE. SSE is an HTTP-based server push technology that allows clients to automatically receive updates from a server. With SSE, a client establishes a persistent, long connection with the server. Through this connection, the server continuously sends data to the client. It's important to note that clients cannot send data back to the server via SSE. Here's how SSE works. The client creates a new event source object to request and open a persistent connection to the server. Once the server accepts this connection, it keeps it open. Whenever there's an update on the server side, it sends data update events through this connection. As the connection remains open, the server can send more events anytime. The client listens to these events to receive data updates. Now let's delve into the advantages and limitations of SSE. Advantages. 1. Simplicity. Implementing SSE on the client side is straightforward, as most modern browsers natively support the event source interface. 2. Efficiency. Since the connection is persistent, the server can send data anytime without frequent requests from the client, reducing HTTP request overhead. 3. Automatic reconnection. If the connection is accidentally closed, the event source interface automatically tries to reconnect. Limitations. 1. Limited browser support. Although most modern browsers support SSE, it may not be supported in some older or certain mobile browsers. 2. Text only. SSE supports only text data, making it unsuitable for transferring binary data. 3. Unidirectional communication. SSE supports only one-way data flow from server to client. If bidirectional communication is needed, other technologies like WebSockets might be considered. Suitable scenarios. Given these points, SSE is particularly suitable for applications where the server needs to continuously push data to the client, but there is no need for data to be pushed from the client to the server, such as 1. Real-time news feeds, automatically updated news headlines or blog posts. 2. Live sports updates, real-time updates of scores and stats during games. 3. Real-time data in stock or forex markets, live streaming of stock prices or trading information. Application examples. Let's explore two typical scenarios where SSE is used. An interesting example is ChatGPT, a well-known artificial intelligence product in recent years. Many might not realize that SSE technology is used behind the scenes when interacting with ChatGPT. For instance, when you ask ChatGPT to write an introductory article about server-sent events, once you submit your request, the server begins processing and gradually generates the article. The generation of the article is typically done in batches, not all at once. During this process, ChatGPT's server uses SSE technology to push parts of the article to the client in real time. Thus, if the response content is extensive, you might notice ChatGPT's replies appearing in a step-by-step manner, leveraging SSE technology. Another typical application is the dashboard of an enterprise monitoring system, which can implement real-time data updates via SSE. Take Netflix's open-source Hystrix as an example, a widely recognized component for microservice monitoring and circuit breaking. Hystrix comes with a web dashboard that displays real-time performance metrics of monitored services, along with details on circuit breaking. This dashboard uses SSE technology to push performance data in real time. For a specific demonstration of the Hystrix dashboard, you can refer to a video posted on YouTube 10 years ago by Ben Christensen, the creator of Hystrix. In the video, he shows how Netflix internally uses the Hystrix dashboard to monitor real-time performance metrics and circuit-breaking situations of core services. The demonstration is very visual and effectively showcases the capabilities and practicality of SSE technology in real-time data pushing. Next, let's discuss WebSocket technology. WebSocket allows for full duplex communication over a single persistent connection. Unlike HTTP, once a WebSocket connection is established, it remains open, allowing data to flow bidirectionally between the client and server at any time without needing to re-establish the connection for each exchange. Let's look at the WebSocket interaction flowchart. The client begins the handshake process by sending a special HTTP request. This request informs the server that the client wishes to upgrade the connection to WebSocket. If the server accepts the request, it confirms with an HTTP response, signaling the upgrade from HTTP to WebSocket. Once the protocol is upgraded, a full duplex communication channel is established, and the client and server can start transmitting data in both directions. This connection remains open until either the client or server decides to close it. It's important to note that WebSocket uses a specific protocol for communication. This protocol is identified by starting with WS for its unsecured version and WSS for its secured version, instead of HTTP or HTTPS. Now, let's analyze the advantages and limitations of WebSocket. Advantages. 1. Low latency communication. The persistent connection of WebSocket reduces overhead and latency, making it particularly suited for applications that require fast responses. 2. Full duplex communication. Clients and servers can send and receive information simultaneously, enhancing interactive efficiency. 3. Reduced server load. Maintaining one persistent connection saves more resources than repeatedly establishing connections for each interaction. Limitations. 1. Compatibility issues. Although most modern browsers support WebSocket, some older systems might not. 2. Security considerations. WebSocket may introduce security risks as the persistent open connection is more susceptible to certain types of network attacks. 3. Resource usage. If not managed properly, long-lived connections could lead to excessive use of server resources. Suitable scenarios. Considering these points, WebSocket is particularly well suited for the following scenarios. 1. Online gaming. Enables rapid updates of game states and interaction among players. 2. Chat applications. Allows users to send and receive messages in real time. 3. Financial applications, such as stock trading platforms where users need real-time market data or to execute trades. 4. Real-time notifications, for updates like social media or live news event push notifications. Application examples. Now let's explore the application of WebSocket in a real-time chat scenario. Imagine Mike and Jane are preparing for a real-time chat. Using WebSocket, they first need to establish a connection with the server, beginning with the WebSocket handshake phase. Once the handshake is successful, Mike and Jane each establish a persistent WebSocket connection to the server. This allows communication between them and the server to be bidirectional. Suppose Mike and Jane both join chat room number 01. When Mike wants to greet Jane, he might type, "Hey Jane," and this message is sent from Mike's client to the server, which then pushes it to Jane's client. This way, Jane can see Mike's greeting in real time. WebSocket supports not only real-time message transmission, but also allows full duplex communication, meaning Jane can also send messages to Mike at the same time. Through this simple chat example, we can see how WebSocket effectively supports bidirectional real-time communication, significantly enhancing response speed and user experience. Now, let's explore WebHooks, a communication mechanism that allows a server to send data to a specified URL when a certain event occurs. Unlike techniques that require the client to initiate a connection and query, webhooks are server-initiated, event-driven pushes of data in real time. This means that with webhooks, the client must also handle HTTP requests, effectively acting as a server with an externally accessible URL. Here's how webhooks work. Users first register a webhook on the server, including specifying the target URL for receiving data and subscribing to the events of interest. When the registered event occurs, the server automatically sends an HTTP post request to the target URL. Then the client can receive and process the data from this post request accordingly. Let's look at the advantages and limitations of webhooks. Advantages. 1. Real time. Webhooks provide an extremely efficient way to transfer data, notifying the recipient immediately when events occur. 2. Simplified architecture. By using webhooks, complex polling logic is avoided, reducing the client's querying load on the server. 3. Easy to implement and maintain. Webhooks are relatively simple to set up and maintain. Limitations. 1. Dependence on external services. If the server receiving webhooks is unavailable, event information might be lost. Therefore, the server side usually needs to support error retries. 2. Security concerns. It's crucial to ensure the security of data transmitted via webhooks to prevent man-in-the-middle attacks and data breaches. 3. Capacity limits. If events are triggered too frequently, the receiving server must have adequate processing capacity to handle potential high concurrency requests. Additionally, slow client reception might consume significant server resources or even lead to blockages. Suitable scenarios. Webhooks are particularly suited for scenarios such as 1. Automated tasks. For instance, automatically updating social media after an article is published in a content management system. 2. Integrating third-party services. Notifying merchants to process order statuses after transactions are completed on a payment gateway. 3. Monitoring systems. For real-time system alerts, such as server downtime or performance anomalies. Application examples. Consider Shopify, a globally renowned e-commerce platform that supports webhooks through its API, enabling real-time data synchronization from Shopify stores to external systems. Imagine a merchant operating an online store on Shopify, wishing to synchronize store data in real time with another external system. Typically, the external system would need to continuously poll Shopify's API to check for new orders. Although this method is direct, it generates a high volume of ineffective requests and places significant load on Shopify's servers, particularly when thousands of external systems are polling simultaneously. To address this, Shopify recommends using WebHooks. In this setup, the external system first registers a URL on Shopify's platform to receive data and subscribes to events of interest, like order creation. Once an order is placed in the store, Shopify automatically pushes information about the new order, usually in JSON or XML format, directly to the registered URL of the external system. This ensures timely event notifications while significantly reducing network overhead and server load. This example illustrates how webhooks can effectively optimize the data synchronization process, making event-driven notifications more timely and efficient. Thank you for watching today's video. Today, we explored 4 real-time communication technologies: HTTP polling, including long polling and short polling, server-send events, SSE, WebSocket, and WebHooks. I hope this video has helped you understand how they work, their advantages and disadvantages, and their appropriate use cases. Whether you're a developer or just someone interested in these technologies, understanding these communication mechanisms will help you choose the right technology for your future projects. Remember, each technology has its unique applications and limitations, so it's important to consider the specific needs of your business when making a selection. If you liked this video, please give it a thumbs up and subscribe to our channel for more content related to system architecture and design. If you have any questions or would like to discuss further, feel free to leave a comment. Thank you for watching, and I look forward to seeing you in the next video.